Statistical inference is the most important thing that we will learn in this entire class. It is the heart and soul of statistics. So we're going to work through this nice and careful because this is it. This is the core of this whole entire class. In statistical inference, we use a sample to learn about a population. That's it. Now, this sample must be randomly selected from the population. We need to have a simple random sample, which, what does that mean? Well, that means that every single person in the entire population or thing or tomato plant or car or whatever it is we're studying, everything out there in the entire population must have exactly the same chance of being selected for the sample as everything else. And if we don't have that, if this isn't completely random, if some members of the population are more likely to be selected for our sample and some members are less, well, then we have bias. Bias in this course, bias means we have a non-random sampling method. It's not completely random. And as a result, if we have a sample that's not gathered truly randomly, well, then no, we can't do any of this. Everything we're studying here goes right out the window. It does not apply. We can't use a sample to say things about the population unless it is truly gathered in an absolutely random way. Now, the honest truth is in reality, it's really hard to gather a random sample of a large population. That's a tough thing to do. And so often when a study is done, well, there are some biases that creep in. But if we're presenting that to the scientific community, we're upfront about this. Okay, here's what we did. Here's what we got for our sample. And then, our audience can decide whether they want to believe that this is a pretty good random sample or not. All right, in this, statistical inference consists of two things, ladies and gentlemen. Count them, two things. One, there are hypothesis tests. A hypothesis test is where we evaluate whether some specific statement about the population is likely to be true based on our sample. We want to see, does this sample go well with this statement? Or, whoa, no, a sample like this really wouldn't happen if the statement was true, and so the statement does not be true. We're going to work through that. The other big thing we do in statistical inference is confidence intervals. We make a confidence interval. We take the sample and we say, okay, we got this result from our sample, which is probably decently close to what the overall result for the population is. But what does close mean? So we try to put a range on that and we say, okay, based on this, we think for the whole population, we're 95% confident it's going to be somewhere in this range. Let's do these specifically and in detail. All right, so we need a scenario. We need a real world applied sort of thing. Suppose we're doing a political poll. We want to know the proportion of voters planning to vote for candidate A over candidate B. So we've got just two candidates in this, and we want to know P. P is the true proportion of all voters out there in the whole entire population, all the voters out there, and we want to know who's actually going to vote for my candidate, candidate A. So step one is gather a random sample of our voters. Well, in reality, that's the super duper hard part. I mean, man, it's hard to get a random sample of voters. How do you do that? Well, you can call people on the phone, but a lot of people refuse to participate. People refusing to participate, is that equally likely among supporters of different candidates? Well, maybe. I don't know. It's messy. It's complicated. Of course, some people have gone to cell phones these days, so, you can only call people's landlines for a poll. It's messy, it's complicated, but we're just gonna skedaddle right past that complexity of how we gather our sample. Let's just assume we did this. We gathered a sample of 200 likely voters, then by some strange deep dark magic, we actually think that this is a pretty good random sample. We then ask each and every one of these people, each of these 250 people, who are you planning to vote for? Suppose we find that 145 of the 250 people are planning to vote for candidate A. What's the first thing we do? Well, we compute the proportion of our sample planning to vote for candidate A. 145 out of 250 people, we divide, we get 0.58. Now that is our P hat. Notice that there's a little hat symbol over the P. This is really important. We're going to put a hat over it because we're talking about our sample, these 250 people we talked to, and not the whole population of all the voters out there that are going to go to the booth on election day. That would be P without the hat. That's the whole population. So in this case, 58% is our point estimate. That's our best guess. That's our best estimate of what it is for the whole population, but we don't know what that is exactly. All right, so 58%. That's a majority, right? Do we conclude that candidate A will be the next governor? Shall we tell that person to start writing their acceptance speech? No. This is the sample, not the whole population. This is why we need statistics, inferential statistics. If somebody else went out there and did this study for themselves, gathered a different sample of a different 250 likely voters, they would probably get at least slightly different results. So I want to know, are my results statistically significant? Can I say, yeah, you're ahead in the polls, or is our margin of error on this? I mean, is somebody else likely to go out there and get 40%? I don't know. We're going to have to do math. It kind of depends on our sample size and a lot of factors. So we're going to work through this in detail. But the point is, we need to do math because at this point, we don't know whether this is statistically significant or not. All right, so this is it. First of all, the data we're dealing with is binomial data, meaning that each person we talk to gives me one bit of information. All voters say either yes or they say no. So this is binomial data, so that allows us to do this. Later on in the course, we're going to talk about numerical data and all sorts of other sorts of data we can deal with. But right now, we're dealing with binomial data. Every person just says candidate A or candidate B. The results from every person fit into one or of two categories. So this is what happens when somebody says true or false, yes or no, do you like cats or do you like dogs, Coke or Pepsi, you know, that sort of thing. Everybody's vote comes into one of two categories. Again, P, without the hat on it, is the true proportion of the whole population. That's everybody's going to vote in the whole state. P hat is the proportion of our sample, just the 250 people we talked to. Again, so here's a scenario. Suppose we imagine that lots and lots of people go out there and they replicate our study. Everybody goes out there and gathers a different sample of a different 250 voters. Each person then computes their P hat. So every different sample would give us a different value of P hat. We could make a histogram out of all these different P hat values. And what we would find is that histogram would be normally distributed as long as certain conditions are met. As long as, one, our sample size is at least about 30, and two, that we have at least 10 people in each category. In this case, 10 people saying they support candidate A, and 10 people saying that no, they support candidate B. 10 people in each category. If those conditions are met, then everything we do in this presentation here can apply. We can use the normal approximation to binomial data, and all this works and is glorious. If not, then we got to go back and we have to use straight out binomial stuff, the p-binom command in R and stuff like this. But here, the conditions are met. That makes things nice and wonderful and glorious. And so we know that if many, many, many people did this, and each one got their own p-hat value from their own sample of the different 250 voters, these would form a nice, beautiful bell curve normal distribution. And the standard deviation of p-hat the standard deviation of that would be, the magical equation is the square root of p times 1 minus p divided by n, and then the square root of that whole thing. All right, the first thing we need to grapple with is the null hypothesis. Now, the thing is, we're working for candidate A. We think candidate A is a wonderful, glorious, wonderful candidate that will make our state be good. We want to conclude that A will win the election. But science is all about skepticism. It's not about just believing what we want to believe, but no, we have to look at the other side of the coin. What would somebody else say? What would somebody else argue? So we have to consider the possibility that we're wrong and that we happen to get a majority of our sample supporting A just by random chance. We're going to evaluate, is that likely? The null hypothesis, that's the skeptic's perspective. Assume that you're wrong. Assume that there's no effect here. Assume that there's nothing to see. Assume that the cancer drug doesn't work. Assume that this brand of fertilizer doesn't increase tomato production. Assume that there's nothing to see here. So in this case, null hypothesis would be, candidate A doesn't have a majority. The election's just tied out. That would be kind of the most boring result we could get. So we write this in hypothesis testing. We have very, very specific, proper mathematical symbols that we use to describe this. So everybody knows what we're talking about. So to write the null hypothesis, I put down a capital H, and then as a subscript, I put a 0, because this is the null hypothesis. Null, from the Latin nullis, meaning nothing. The null hypothesis, then I put a colon to tell me what it is. In this case, it's P equals 0.5. That would be the most boring, annoying results we could get out of this. Then we would learn nothing, right? So the null hypothesis, note, is a statement about the population, not the sample. I know what the sample is. The sample said 58%. I know what p hat is. The null hypothesis involves p, not p hat. All right, now let's consider the alternative hypothesis. This would be the good news. That's what I want to conclude. I want my data to be interesting. I want it to be meaningful. I want it to tell me that the drug cures cancer, that the cream regrows hair on bald men, that this fertilizer causes corn plants to produce more than ever before. This is what we want. We want our sample to tell us something important, interesting, and useful about the population, and we're desperately hoping that our data supports this idea. So in this case, because the null hypothesis says p equals 0.5, in general, there are three possibilities for what we could choose for the alternative hypothesis. So we do a capital H, we do a little subscript a because it's the alternative hypothesis, we do a colon, and then we could say that, all right, the null hypothesis says p is equal to 0.5. We could say that p is greater than 0.5. We could say that p is less than 0.5, or we could just say that p is not equal to 0.5. In each case, whenever we do a null hypothesis, we have to choose which one of these three possibilities makes the most sense in this context and would allow us to say something interesting. Now, in this case, p being less than 0.5, that's not what I want. That's not what I want to do. P not equal to 0.5, well, in that case, it would be just if I was trying to demonstrate that it was anything other than tied. That's not what I want. I want P greater than 0.5. That would allow me to say something interesting. The results I'm rooting for, the results I want to conclude are that candidate A is leading the election, is going to win, is going to be the next governor of the state. So in this case, we select the alternative hypothesis, H sub A, colon, P is greater than 0.5. All right, so here are our hypotheses then. The null hypothesis in words is the election is tied, no one's ahead. H sub 0 says P equals 0.5. That's kind of the most boring, the most annoying result we could possibly get. That's the skeptic's perspective. The alternative hypothesis is what I want to conclude. I want to say, yeah, we learned something here and it's cool. In this case, candidate A has a majority and will win the election. So the alternative hypothesis, capital H subscript A, is that P is greater than 0.5. Again, note, both of these hypotheses, they're statements about the population, not the sample. So notice there ain't no hats on those P's. They involve P, not P hat. I don't need to make any hypotheses about P hat because P hat is the sample proportion. I know what the sample is. The sample is the data we have in our computer. We're studying it. In this case, we know precisely and exactly what p hat is. P hat is 0.58, 58%. I don't need to hypothesize about that. That's why the null and alternative hypotheses are always about the population, P without the hats. All right, so now let's do the math. All right, the whole logic of all this, the central organizing logic of hypothesis testing is we assume the null hypothesis is true, and then we calculate, well, what's the probability we would get a sample kind of like what we got? What are the chances we would get something like 58% if the true population was 0.5? What are the chances of that? If we say, whoa, holy cow, look at this. If the true population was 50%, a sample of 250 would be really unlikely to get 58% or better. You know, maybe 1 in a million chance of that happening. Then we'd say, oh, we did the study, and we get a result that would happen only 1 time in a million if the null hypothesis was true. So the null hypothesis is not true. So then we would reject it. We accept the alternative hypothesis. Life is good, wonderful, good stuff. All right, that's what we're going to do. Now let's do the math. Step 1 is we need to calculate the standard error based on the null hypothesis. Remember, the essential logic of this is step 1 is assume the null hypothesis is true. So the null hypothesis is that it's 0.5. So we calculate our standard error. That's going to be the square root of 0.5 times 1 minus 0.5 divided by square root 250. We take the square root of the whole thing and we get 0.0316. This would be the natural variability that we would expect. We would expect that if the true population mean was 0.5, your sample p-hats are going to go above and below that by about 0.03. About half the time you get a p-hat bigger than that. Half the time you get a p-hat smaller than 0.5, and they would vary with a standard deviation about 0.03. Step 2, we calculate our test statistic that measures the distance, the discrepancy between, in this case, our null hypothesis, which says that p is 0.5, and then our p-hat, which said was 0.58. That difference, that 8% difference, we want to measure how big that difference is in standard errors. So we take our p-hat minus the p we get from the null hypothesis. We do 0.58 minus 0.5, there's the 8%. We divide that by 0.0316, and we get 2.53. Now this is a z-score, a z-value. We know what that is. That's the number of standard deviations away from the mean. In this case, 58% is 2.53 standard deviations, standard errors, above where the null hypothesis says we should be. And then we say, well, is that likely? Would stuff like that happen commonly, typically, if it was true that p was really 0.5? So step 3 is we evaluate this probability by calculating a p-value. Now, p-values are important. They're vital. They're awesome. They're fantastic. They're the center. They're the center of this whole hypothesis testing thing. So here are some words that are really important. A p-value is the probability that we would get the results we got or something more interesting, something more extreme, assuming that the null hypothesis is true. I think you should learn those words by heart. That's really, really, really important. A p-value is the probability that we would get the results we got, whatever they are, or something more interesting, something more extreme, assuming that the null hypothesis is true. A p-value is essentially the measure of how weird would our results be if the null was true. How strange, how bizarre. So what it is, so therefore, the p-value is always the tail of the distribution. So we got a little graph here that, it's a rough sketch of this normal curve distribution sort of thing. A p-value is always the probability of getting what we got or more. So it's always a tail of the distribution. In this case, they got up there in green shaded. The p-value is the probability of being to the right of this. So we want something more extreme. P-value never includes the body, the central part of that, because that's not what a p-value is. P-value is the probability of getting what we got or more extreme. So if we were to the left of the mean, if we had a negative c-value, then the p-value would be to the left. Whatever it is, it's the tail. It's from where we hit and then farther away from the center. So as a result, if z was positive, which is what we got in this case, then this is the area to the right. So in R, let's see, well, p norm always gives me areas to the left, so I want areas to the right. I got to subtract them from 1. So if z is positive, I want the area to the right. So in R, we compute the p-value with 1 minus p norm of whatever z test statistic I got. On the other hand, if z is negative, if my test statistic was a negative number, well, then I would want the area to the left. So in R, we would just compute the p-value with straight out p norm of z. Now, the other interesting wrinkle is that if I had a two-sided alternative hypothesis, well, in this case, that would be the alternative hypothesis would be that p is not equal to 0.5, well, then it would be important to me. It would be just as interesting to me if I was extreme to the right as extreme to the left. So whatever we get from whichever tail we get, we would then take this and double this to get the p-value. So that happens if I have a two-sided alternative hypothesis. If my alternative hypothesis says that this doesn't equal something, then I would, once I do my computation with R, then I multiply that by 2, because I would have been just as interested to get something above on the positive sense as what I've been to get on the negative sense. All right, so in this specific case, our p-value, in this scenario, we got a p-value estimate of 58%. This corresponded to a test statistic of z equals 2.53. So our p-value, this would be the probability of getting 58% or more in our sample supporting candidate A in our sample of 250. Or in other words, a z-value of 2.53 or more. Again, assuming that the null is true and that in the whole population of voters, it's the most boring result possible. The race is tied 50-50. We compute this specific number, in this case, with R as 1 minus p norm of 2.53. We don't double it. We don't multiply it by 2 because our alternative hypothesis is one-sided. We only care if p is greater than 0.5. And so we get 0.0057. That's small. Look at that. That's less than 1%. That's a very unlikely result. If we get a really small p-value, here's the logic. If we get a really small p-value, it means that, well, results like ours would be very unlikely to happen if the null hypothesis were true. If the null hypothesis were true, there'd only be a 0.0057% chance of getting what we got or more extreme. And we got it. We did the study once. We talked to one sample of 250 voters, and this is what we got. So, and I got a result which should only happen less than 1% of the time. So what does that mean? That means the null hypothesis is probably not true. If you do a study once, you're probably not going to get fantastically unlikely results. I was born in the dark, but it wasn't last night. As a result, yeah, okay, this result would be really unlikely if the null were true. So we reject the null hypothesis. We have strong evidence here that the null hypothesis is not true. On the other hand, suppose I got a large p-value. Suppose I got, I don't know, 50%. Well, that would mean results like this would be common, would be typical, would be average, ordinary. That'd be the sort of thing you would expect to get if the null were true. So in that case, we can't draw any conclusions and we could not reject the null hypothesis. All right, so we need now a threshold. Okay, if the p-value is really super duper small, 1 in a million, then we say, hey, results like this would almost never happen if the null hypothesis was true, so our data means the null hypothesis is probably not true. If the p-value is big, it's 0.5, it's 0.6, then we would say, well, you know, the results we got would be typical, common, average, ordinary results if the null hypothesis were true, so we can't reject the null hypothesis, so therefore we need a threshold. Exactly how small does that crazy p-value need to be in order to reject the null hypothesis? We call this threshold alpha, after the first letter of the Greek alphabet, alpha. Typically, the most commonly used value of alpha in various scientific studies is 0.05, 5%. You will find published studies where they use an alpha of 0.1 or 0.01 or 0.005. Those happens too. So here's how it works. If I get a p-value which is less than alpha, what I say is, wow, these results like these would not happen very often if that null hypothesis were true, and we got it. I was born in the dark, but it wasn't last night. I don't think it's likely that this would happen, so we reject the null hypothesis. We say that difference between p hat, what I got, and p naught, what the null hypothesis said I would got, I say that difference is statistically significant. We reject the null hypothesis. We conclude the null hypothesis is false. We learn something. We accept the alternative hypothesis. On the other hand, if I get a p-value larger than alpha, more than 5%, then results like ours would not be unusual. That wouldn't be surprising. That's the sort of thing you would expect to happen all the time if the actual null hypothesis were really true. So what do? We fail to reject the null hypothesis. We say that our difference between p hat, what we got, and p from the null hypothesis, that's not statistically significant, and therefore we learn nothing. This does not mean that the null hypothesis is true. It just means that this data doesn't tell us the null hypothesis is false. So I know that's kind of a double negative in there. But no, this really means something. We learn nothing when we fail to reject the null hypothesis. We don't conclude the null is true. That doesn't mean the null is right. It just means this data doesn't tell us anything one or another. It could be the null is true. It could be our sample size just wasn't large enough to bring out the difference. It could be we have unlucky data. We can't draw any conclusions one way or another. So whenever we do a hypothesis test, there are possible errors we can make. We're drawing a conclusion from a sample, from incomplete data. It's just a sample of the whole population. It's not everything. So we might follow the procedure, draw a conclusion, and the conclusion might be wrong. So again, our data only comes from a sample. So there are two types of errors. We call them type 1 and type 2. Type 1 error is what happens when we reject a true null hypothesis. So that means the null hypothesis is true, but I got data which was very far from it just based on bad luck. In this case, the probability of making a type 1 error is precisely and exactly equal to alpha, our level of significance that we choose. So that one's kind of easy to quantify. Type 2 error is a little messier. That's what happens when we fail to reject a false null hypothesis. So in this case, null hypothesis is false. We got some data, but we couldn't reject the null hypothesis. So yeah, we've made a type 2 error. So maybe our sample size wasn't big enough. Maybe we just are unlucky. There's a million things that could cause this. We can't calculate an exact probability of that. With type 1 error, the probability of making it is alpha. With type 2 error, well, I'd need some specific value for the alternative hypothesis and know what the true value is from the whole population and then see whether my sample size is big enough to pick that up. That one's harder to quantify. So let's draw conclusions from our specific hypothesis test in this scenario. So we got 58% of our sample supporting candidate A. We found a p-value of 0.0057. You know what? That's smaller than alpha. That's less than 5%. That's a whole lot less than 5%. That's a really unlikely result to happen if the null hypothesis were really true. So therefore, we reject the null hypothesis that the race is tied at 0.5. That difference between our p hat and our claim about p from the null hypothesis, that is a statistically significant difference. Those two statements mean the same thing. Reject the null hypothesis and statistically significant, those are just two different phrases that mean exactly the same stuff. We therefore conclude that the percentage of the population who support candidate A is above 50%, this sample tells us that yes, candidate A is leading in the polls. It might not be exactly by 58%, but it's certainly above 50%. 50% is wrong based on this, and there's a relatively, so that's what we got. That's what our p-value means. It would be unlikely to get data like this. So now, based on this hypothesis test, we know what p, the p for the whole population, is not. Now, I want to say something about what it could be. All right, we've rejected the 50%. We know we're in the lead. Well, we might be 8 points ahead. We might, 58% we might have a lead, but how much is our lead could be? I now want to make a confidence interval. Okay, so a confidence interval is a range. That's the range of values that where we have a certain level of confidence that would contain the true population value P, the percentage of voters are supporting candidate A. Most commonly, we'll often make a 95% confidence interval. What's the process? Step 1, Step 2, Step 3. Step 1 is calculate the standard error, this time based on the sample p-hat. Notice this is different when we're doing a hypothesis test. And when we're doing a hypothesis test, we use p of 50% from the null hypothesis. Here, we're going to use p from our sample. At this point, we're going to say, I don't even know what p is at all for the whole population. Let's make the best estimate we can. The best estimate we can is 0.58. That's our 58%. So we do the square root of 0.58 times 1 minus 0.58 divided by 250, square root of the whole thing. We get 0.0312. That's a little bit different than we got last time. Step 2, we need a z-value, except this is a different z-value. This is not the test statistic z-value last time, which was a measure of how far p-hat and p were away from each other. This is a totally different one. This is a critical z-value. Don't get these two things confused. This, I'm going to put a little star next to it up there so we don't get them confused. The critical value z star is what we need for our confidence level. In this case, I want a 95% confidence interval, which means I want an interval that has 95% of the stuff inside of it. Well, that leaves 5% of the stuff outside of it, and it can be outside of it on the positive side or outside of it on the negative side. So I want a distribution that has half of that 5%, 2.5% outside of my interval on the positive side, 2.5% outside of my interval on the negative side. So I want to find, well, what z-values would capture, what in a normal distribution, what z-values would capture 95% of the stuff and leave 2.5% out on the positive side, 2.5% out on the negative side. I can get this with two different commands from R. I can go Q norm of 0.975. I want to have 97.5% less than this and 2.5% to the right of it. Or I can go to the other side. I can do minus Q norm of 0.025. Okay, so Q norm of 0.025 is going to give me a negative value that has 2.5% to the left of it, 97.5% to the right of it. And so both of those commands give me the exact same result, which in this case is 1.96. You got to go 1.96 standard deviations above and below the mean of a normal distribution in order to capture exactly 95% of it. So step 3, all right, so this is how far I want to go above and below. That's the number of standard deviations, the number of standard errors. I want to go above and below my best guess. My standard error is the 0.0312. My z star, my critical z value, is 1.96. I multiply those together, and therefore my margin of error is 0.066%. So in order to have a 95% confidence interval, I'm going to have to go 6% above and below my best guess. So here it is. Here's my confidence interval. My best guess was 58%. That's the p-hat I got from my sample. I do 58% plus or minus my margin of error, plus or minus my 6%. So that ranges from 58% minus 6% is 52%. 58% plus 6% is 64%. So my confidence interval ranges from 0.52 to 0.64. So what do I say based on this? We are 95% confident that the true population proportion of all voters in the whole state who support candidate A is somewhere between 52% and 64%. That's a really important sentence. That's absolutely huge. That is the I want you to be able to compute a confidence interval. I mean, to do the math, that's important. But at least as important as that is to be able to interpret the meaning of a confidence interval. A confidence interval is telling me something about the population, in this case, the population of voters, and the proportion of voters, in this case, who are likely to support candidate A. Based on this data, I estimate that I'm 95% confident that between 52% and 64% of all the voters in the whole state support candidate A. Now, if you want more details on that, so that statement is gold. That statement is wonderful right there. If you want a little bit more detail, you want to scratch deeper, well, what does that 95% confident really mean? Okay, in a deeper level, a probability and statistics level, what that means is if many people, say many thousands of people, were to do this exact same study, each gathering a different sample of a different 250 voters, and each were to create their own different confidence interval, some of them are going to be higher than mine, lower than mine, and all of these, so I now have thousands and thousands of confidence intervals. It's done by thousands and thousands of people. Based on probability, I would expect that about 95% of these confidence intervals would catch the one true population proportion, the real right answer, P, and about 5% of these confidence intervals would not have it. They would be, though their range would be too high or too low. They wouldn't catch our true population proportion within them. All right, so here's a summary. We've learned a lot. Wow, this is huge. Statistical inference is the process where we use a randomly gathered sample to learn about a population. And the important less limitation on this is that it has to be randomly gathered. If it's not randomly gathered, well, then everything goes out the window. There are two things we do in statistical inference, two really big things. One, we do hypothesis tests. We evaluate whether a specific statement about the population is likely or unlikely based on our sample. Then the other thing we do, thing two, is we make confidence intervals. A confidence interval is a range that describes where the statistic for the population is likely to be, where we can say with 95% confidence that it's likely within this range. When we're doing this, it's really important to consider the null hypothesis. This is the skeptic's perspective. We assume that we're wrong, that our data doesn't tell us anything interesting, that we just have, our results looked interesting, but we just happen to get slightly interesting looking results by chance, random stuff happens. We're never going to get the population exactly on the nose. So then based on that, we do our calculations. A p-value is the probability. It says, well, what's the probability we would get the results we got or something more interesting, more extreme, assuming that the null hypothesis is true. If our p-value is really super duper small, then we say, hey, our results like this would be crazy unlikely to happen if the null hypothesis were true. So then we can reject the null hypothesis and draw some conclusions and accept our alternative hypothesis, and that's what we want to do.